you guys whenever you want it. Again, my flyer's up here. I'm going to leave some at the front as well. I hope we can see you guys there, and I hope you guys have a great semester. All right, thanks.
So yes, please make use of these times work. Please do show up to that. That is one of my biggest critiques with this style of course. It's outside of my control. This is how the university has assigned this. Is basically I don't get to interact with you on very much of an individual level unless you come to office hours. And that's really where you're going to do a lot of your learning is outside this class. I give you all the content, but the learning is going to happen when you actually engage with it, spend time with it. And having someone that can give you feedback while you're going through problems, or that can provide it. Because one of the challenges with learning this content is sometimes you don't know the questions to ask yourself when going through it. And that's what the tutors can really help you with, is those guiding questions, the things to think about, the lines of thought. So there's this at some point later. It's going to be a little bit later. They open, I think, the third week. There's something called the Physics Help Room, which is located in Physical Sciences Building. I think it's room 158. It's the room that when you go in the front door of Physical Sciences Building, it's directly to the left. And they have tutors in there the entire time, and pretty much all of them can help you about the entire week. So there's always someone available. And again, my office hours, please come to me during my office hours. That's what I'm there for. Would love to work with you and help you throughout whatever it is. And it can be anything. It can be class related, outside of class related. It doesn't matter to me. Happy to help. Okay. So we finished last class. We talked about charges. And I'm going to switch to my computer. I apologize because I forgot to hit record last time. So unfortunately there was no video for the lecture last time. But I did hit the button this time. So it is working. So there will be a video of this if you want it afterwards. Whatever. Same with every class. So last class we talked about charges. We said opposites attract, like charges repel. We talked about dipoles and how you basically can induce a dipole in a material. And insulator, you can pull that electron cloud a little bit. But now we're going to get into the actual math behind it. So basically someone observed this stuff. They said these things are repelling each other or they're attracting to each other. And so then they came up with an equation which described how that interaction behaved mathematically. Given various values, figuring out what the forces were based on that. So that equation, and again I quickly mentioned this to you all at the end of last semester, is this one here. This is called Coulomb's law. This is going to be very important. This is one of those fundamental kind of things that we're going to be, again, governs a lot of how the world works. And it looks complicated, so I'm going to go through every single one of the variables and just remind you all what they are. I said them again very quickly last time, but didn't really get much time on them. So this K is Coulomb's constant. This will pretty much, in every single one of every problem you do, that's just going to be a number you're going to plug into the equation. Where does this number come from is kind of an interesting thing. Again, remember when I mentioned that pretty much everything we're doing is just observing what's going on in the world, and on some level you kind of make things up. You say at some point that a meter is this big, and then we just use a meter as that big. We say a charge for Coulomb is this amount of charge. This constant is the thing that we then throw in to actually make certain our result matches. So if we just left it as Q1, Q2 over R squared, the force would not be appropriate. It wouldn't be the right value, so you just include this number and that scales it up so that it actually is accurate. That's why it's in the equation. Again, it's an experimental thing that just is to make the units all work together to actually get you an answer that makes sense. So that's that. Then Q1 and Q2, those are the charges. So for us to have a force, you have to have two charges. A charge cannot generate a force on itself. If a charge could generate a force on itself, that would mean that the charge would cause an acceleration on itself, which means the charge would be moving who knows where. Again, I don't know what that would look like because it's not how the world works. You have to have at least two charges, because that means one charge is going to cause a force on the other charge, and the other charge is going to cause a force on the first charge. One thing you can see here is that so for instance, here I have charge 1 and charge 2. So this Q sub 1, Q sub 2, that's just a way of defining them. Charge 1, charge 2. It doesn't really matter which one's which. Because the force is going to be identical on both of them. It's just going to be opposite in direction. So this is one of Newton's laws. For every force, there's an equal and opposite force. If one of the charges is pushing on the other one's pushing on the first one with the exact same amount. Doesn't matter if one's twice as big, doesn't matter if it's 3 times as big, exact same amount. So those are that. So we have the constant, we have the charges. I'm going to move to the bottom one. This is just the distance between the charges. So this R, and I'll do it over here to the right, left because I have more room. Distance between charges. The reason it's in those vertical brackets is because it is given here as a vector, because technically you're going to the direction between them is going to matter, and we're going to incorporate that later on, which is why we don't. So by taking those brackets, those absolute values, we change it from a vector to a scalar. The reminder, if you all don't remember the difference between vectors and scalars, this was something I remember when I was going through my undergrad that it didn't make sense until, I don't know, second, third year. I could do all the math. People kept saying vectors and scalars, took a long time for it to cement. A scalar is just a number. Scalar is like saying I'm going 30 miles per hour. That's it, just I am going 30 miles per hour, done. A vector is 30 miles per hour in a specific direction. So a vector is saying I'm going 30 miles per hour east. Now not only do I have a value, but I have a direction. So we're going to be working with vectors and scalars in this course. As you go into engineering, you're going to have vectors and scalars. Because sometimes scalars are the appropriate thing and sometimes vectors are the appropriate thing. When we talk about forces, you have to have the vector component because that tells you which way it is. If I say I have a force of, for instance, I have some object and I say there is a force of 30 newtons, another force of 20 newtons, another force of 10 newtons. You can't add those forces unless you know what direction they're going. If they're all pointed the same way, great, then they're all going to add the same way, no problem. If one of them's pointed the other way, though, it's going to have a profoundly different effect on the problem. That's why vectors are super important, and when you need them, that's why in this case, this is a vector because it's a force. This r hat points in the direction of r, okay? So you may have seen these r hat vectors before. They're called unit vectors. And really all this unit vector, the whole reason it's in this equation is it just tells you that the force is pointing in the direction of r. The value of this unit vector is 1. So it has a value of 1, so it contributes nothing to the final number, but this is completely where the direction comes from. That's why we put it there. So in the case of this problem up here, we have r. So we say that the vector r can kind of go either way, and it's going to depend on which one you're trying to find the force on. So for instance, if we're trying to find the force on 1 due to 2, the force vector, so r is going to be measured from 2 to 1. So this would be that r vector. And I'm going to do of 2 on 1. So we put the first one, so it's 2, then 1 because it's force of 2 on 1. And I'll clarify that. 2 on 1. So R21 points that way. R12, again, I'm unfortunately a little tight here in space. R12 points the other way. Then when you plug in, because they're both positive vectors, they're both positive values, that gives you a positive value, which means it's going to point the direction of R. Again, a lot of this is extra explanation, which I kind of want to talk about because it's really important for you to know what this R hat looks like. You're going to see unit vectors in your future classes. Whenever you see that hat, that just says it is an arrow pointed in that direction. But really, when you're doing these problems, all you have to remember is that the forces are going to be away from each other if they're the same charge, or towards each other if they're opposites. So that's a really quick way of doing it, but I kind of went through more of the notation stuff here because you're going to see it again. You need to remember that. You need to know that if you didn't see that before. Okay, so that's it. That's the equation. Constant times the charge 1 times charge 2 divided by the distance between them squared. Then if you want to get the direction of it, you just draw an arrow. Again, if they're the same charge away from each other, if they're opposite charges towards each other. All right. One thing, actually we'll just move into this next one real quick, and then I'll kind of clarify another point. So I have posted the clicker, there you go, see, you can see that they are posted. I've posted the clicker scores for this last class. They are not part of your final grade, they're just to check if your clicker is working. I'm going to continue to update the roster in the next few days as we lead up to Wednesday. So if you haven't registered it yet, that's fine. It will update. It'll be great. And hopefully this starts. There you go. I'll let you all think on this problem while I'm figuring out technical thing. So here we go. The problem is the charge on sphere 2 is twice that of sphere 1. Which vector below shows the force of 2 on 1? This doesn't work, I'll just shut it down and open it. Woo! Alright, great, there you go. Still AA, it's always going to be AA. I'll close this at some point once we've done enough of these things that you all have it set in stone. So in this problem, it shows two charges. The one on the left is labeled 1, the one on the right is labeled 2. The one on the left has just 1 plus sign, the one on the left has 2 plus signs, signifying it has twice as much charge. And it shows that the force of 1 on 2 is to the right. What is the direction and the amount of the force of 2 on 1? Alright, yeah, feel free to discuss this if you want. Check your answer to the person next to you. Maybe you feel really confident, and then the person next to you has a completely different answer, and then you're like, oh crap, I did it wrong. Or they realize, oh crap, I did it wrong. Alright, again, 5 more seconds. So 5, 4, 3, 2, 1. Alright. So, I'm going to show this answer 2 ways. 1, just conceptually. You can do it immediately conceptually. Or 2, you can do it mathematically. So, we just saw that the equation, so this one is kind of hard to write the knowns and unknowns. So I can't quite do that same thought process, but I'll describe to you how I do this. I look at this, I'm like, oh, 2 charges, I'm trying to find the force. So, I remember the equation for that is F equals K Q1 Q2 over R squared. So if I wanted the force of 1 on 2, and there's technically the vectors, so I'll put those here. So there's that. So force 1, 2 is going to be K, Q1, Q2 over R squared, which then I can just make to K, Q1 times 2, Q1, because I know the other one's twice as much, divided by R squared, and again I have that R hat there. Force 2, 1 is going to be the exact same equation. Why is it the exact same equation? Because I'm trying to find the force of 2 and 1, so I need the second charge in there and the first charge in there. Technically, I suppose I could flip which direction these are, put the second one first and the first one second. It doesn't really matter because it's multiplication. But this is where we need to remember it's going to be negative. Why is it negative? It's because in this problem so R and I even put this here, R 1 2 2 1, R 2 1 is going to the left, so it's a negative value. So that's why I put it as negative. But the long and short of this is that F21 is equal to negative F12. So that's the mathematical way of viewing that. Maybe that's useful for you. The other way is that, remember I just said that if you have charges that are same sign, they're going to point away from each other. One thing I did here that I also really want to note, and this is an error I saw a lot of times last semester, whenever we're doing these forces, so if I want the force on 1, I'm going to start the tail of the vector at the place where the force is acting. So the force is acting on 1, so I start the tail here, and then I draw it in the direction that it's going to go. So in this case, we know opposites repel, so I point the arrow away. But this is the notation we do, is we start the tail of the arrow at the place where the force is acting and draw from there. Now, how big is this arrow? This is where you have to remember Newton's laws. For every force, there's an equal and opposite force. So if charge 1 is causing a force this big on this side, I have to make an opposite force that is identical in magnitude. Identical size. So the answer is B. Because B is the exact same size, but the opposite direction. This is true of every single force in the universe that we understand currently. For every single force, there will be an equal and opposite force. This is why rockets go up. This is why when you push on something, you get pushed backwards. If I was standing on ice and I pushed on this table, I am pushing on it. It is pushing on me. If I was on ice, I would slide away from it. Same exact thing for charges. The same rule that you learned in Physics 1 applies to Physics 2. So, I saw quite a bunch of different answers here, and that's just a reminder. It's really easy to think that it's going to be twice as big because this is twice as big, but they're exact same force. Because if this one's pushing on this one, this is going to push back the same amount. It's one of the laws of the universe that we've observed and defined. All right. Breaking down this, and this is more of a conceptual thing, K technically can be rewritten in other constants. When you're doing the equation, you can just use the value. Oh, and I actually never said the value of K out loud. The value of K is basically 9 times 10 to the 9. So it's a really easy number to remember, 9 times 10 to the 9. And I also didn't say this, but hope you remember the value for, or the unit for F for force is newtons. So remember that. All that to say, so K, 9 times 10 to the 9, it can be rewritten in something that has a bit more physical meaning. It's 1 over 4 pi times epsilon naught. Epsilon naught is something we call the permittivity of free space. And this permittivity of free space, basically, its physical meaning is how easy / difficult, depends on your half full, half empty, how easy or difficult it is to make electric field in a vacuum. We haven't gotten to electric fields. We're going to get to those in a bit. That's why we're going to talk about it more next time. But electric fields, long and short of it, is they're the things responsible for these forces. Charges make them. And depending on different materials you're in, you will have different epsilons. You'll have different permittivities. We are not going to be working in different materials. We're basically always vacuum every single time. If I don't tell you what material you're in, assume vacuum. But I'll say in some of my graduate classes, we started to get to materials that were different. We started to look at how charges would behave, for instance, in metals. And once you start doing that, you have to start to consider this variable a bit more. But in this case, you're not going to have to. You can always assume that's the permittivity of free space. Done. So that's what it means again, and it has this value 8.85 times 10 to the minus 12. So if you want, when you're doing these problems, you can plug in 1 over 4 pi epsilon naught instead, or you can just use K. It's all the same. So you see here, they replaced K with that. It's the same thing though, it's just a number. So I just kind of talk about that because it is important. We will talk about epsilon naught throughout the class, so I need to define it for you all here. Are there any questions at this point? Just kind of want to give you all a chance both to continue writing down stuff, but anything that's confusing to you, anything that seems weird with the last stuff, anything? All right. If you have any questions and you want to ask them outside of class, please do as well. Okay. So this is how you're going to solve problems with this. Whenever I'm saying find the force on a charge due to a bunch of other charges, this is basically the thought process if I've given you point charges. You're going to identify all the point charges in the problem, or any particles that could be modeled as point charge. Basically, if I give you a bunch of things like this, that's a point charge. If I give you a circle with a thing like that, even though it looks like it has a volume to it, we treat it as a point charge. Remember, the definition for a point charge is it has no volume, it takes up no space. And that matters if you're really getting to the nitty-gritty of these things. But I have to draw them as if they take up volume because I can't draw something that takes up no space. That's just not possible. So, that's a point charge. Next thing is draw a picture. I'm going to underline that, like highlight the heck out of this. This is a thing you should be doing in every single physics problem ever if it fits the problem. If you can draw a picture, draw a picture. Every single physicist I know, this is pretty much the first step you do is, if you can, you draw a picture of the problem because it means you don't have to hold it in your head. When you draw a picture of it, it reduces the cognitive load on your brain, makes it so you can look at it and not have to hold that picture in your head, and then you can use your brain for other useful things and figuring out what the picture actually represents and means and all that kind of stuff. Please draw a picture. On tests, I will give you partial case. If For instance, if I told you I had two positive charges separated by a distance of 5 meters from each other, we'll say on the x-axis. This is just a made-up problem. That would mean I would draw an axis. I would pick 2 points, so I'm just going to pick here, and this is 5 meters. There you go, I drew a picture. Now I don't have to hold that in my brain. Now I can look at that and then draw my forces on it, and it's a tool. Unfortunately, we only have so much space in our heads, so try to free up some of it. Okay, so next you're going to define distances and angles. Identify what the problem is asking you to find. Is it asking you for force? Is it asking you for electric field? Is it asking you for none of the above? You're going to draw and label each contribution of the force. So in this case, we're doing forces. Addition in your picture when possible. So this is a reminder that if you have two vectors, that, for instance, I have a vector pointed up and to the right and one pointed to the right, I cannot just add the numbers there. I have to break them into x and y components. Don't worry, I'm going to give you a chance to practice that. And that's the last part, figuring out x, y, z components. They're vectors. It's not just adding the numbers. It's a little bit more complicated. If you don't remember how to add vectors, again, I'm going to quickly do it here, but you're going to need to practice that. You need to know that skill. You're going to be using that, especially mechanical, aerospace, maybe not computer science. If you're modeling any physics stuff, you will, obviously, but outside of that, it's just super important. Okay, so I'm going to make up a problem, then I'm going to have you all do an example. So I will draw 3 charges. So I've got a positive charge up here, I have a negative charge here, and I say, what is the direction of the force? The force on charge 3. I haven't labeled them yet, so this will be 1, 2, 3. Okay, so what is the direction of the force on charge 3? So what you're going to do is basically you're going to consider 2 charges at a time. So I'm just going to ignore this charge up here on top. If I could cover it up, I would, but I can't reach that high on the screen. And I am just going to consider 1 and 3. So if I just consider 1 and 3 first, what is the direction of the force going to be? Well, they're the same charges. They're both negative. So it is going to experience a force to the right. So this is the force on 1 on 3. So 1 on 3, so I put 1 first and 3 second. Okay? Then I kind of have to consider this distance. In this problem, you can assume they're all the same value of charge because I didn't say other. We'll just put that here. So this is Q plus Q minus Q minus Q. There you go. So they're all the same exact value. And in the problem, I'll say this is R and this is also R. The distance between these. Again, I'm just drawing everything, making certain it's all there. I would give you all this information because you can't solve it without it. Okay, so that's that one. I'm going to move this minus Q because it's going to get in the way. Now I look at the next one, so I don't care about number 1, charge number 1, because I'm done with that. So I want to find the force of 3 due to 2. So the force on 3 due to 2. So force of 2 on 3. So just remember, actually you all figure it out. Spend some seconds, see if you can figure it out. What direction is it going to be? How's the size of it going to compare to the other arrow I drew? Spend a few seconds, work with people around you. Then I'll do it and you can check your answer. So we're trying to find the force of 2 on 3. So let's go through, I'll tell you all the thought process and this will let you check it. So we look at them. Are they the same time to charge or are they opposites? Well, they're opposites, so they're going to attract. So as I mentioned, we're going to start the vector at 3 because it's the force on 3 due to 2. And we know it's going to point directly towards 2 because they're going to attract each other. At this point, again, we are ignoring charge 1. Force 2 on 3. Okay, there we go. The next thing I have to do, and I can just do this graphically, so I'm going to kind of draw it down here to make my life easier. Here's my force 2, 3. Here's my force 1, 3. Graphically, you can add vectors very easy. Oh, and one thing I forgot to mention here. So I drew this vector the same size as this one, and this is where I had to remember the math. That the force depends on the magnitudes of the charge and the distance. Well, if these have the exact same magnitude, so this is Q and Q, and the distance is R, well, this one's Q and Q, and the distance is also R, so the magnitude is going to be the same. So F1, 3 magnitude equals F2, 3 because all Q's the same, and R1, 3 equals R2, 3, that's what the magnitudes, equals R. In the picture, they're both R, so R1, 3 is this one, R2, 3 is this one. No vectors there, I just put the values. Boop, boop. Boop, boop. There you go. So then, if you ever want to add vectors graphically, all you do is you put tail to head. And so I can do it either way, so I will just pick one. So I put F2, 3 like this, and then I put F1, 3 like this. And then the net vector is going to end up being, so this is F2, 3, F1, 3. The net vector, I just draw from the first tail to the final head. So F net points that way. So F net is that. There you go. No math here, all conceptual. But this is something you should hopefully be comfortable with. Adding vectors is something you all did extensively in Physics 1. If you are not comfortable with it, that is okay. Please practice. You need to know this skill to be able to succeed in this class. Towards that end, here's some practice. I have given you 4 charges in this problem that are set up in a square kind of situation. And I asked for what is the direction of the net force on the charge at the lower left. The charges, top left charge is just got 1 plus, bottom left charge is 1 plus, bottom right charge is 1 plus, top right charge is 2 pluses, denoting it as twice as much charge as the other ones. Go ahead and utilize those same steps I just did in the previous one and figure out what the direction of the net force is on the charge in the lower left.
Everybody did that. Oh, look at that. Good.
Have a good one. All right. I'm gonna give you all about 10 more seconds or so. Feel like I've gotten most of the responses now. All right, in 3, 2, 1. All right, so we're gonna go through the exact same process last time. So first, what are we trying to do with this problem? We're trying to find the net force. So then we have to recall, how do the forces work between charges? Opposites repel, like charges attract. It's based on how large the charges are and divided by the distance squared. Great, we remembered what we need to remember. Okay, so next thing we're gonna do, there's already a picture, so we don't have to do anything too extra there, but I'm gonna draw the charge down here, and I'm just gonna label these, I don't know, 1, 2, 3, 4. You can make up whatever numbers you want when you're doing these problems. You can call them A, B, C, D, you can call them smiley face, frowny face, sideways face, it doesn't really matter. It's just useful to have some representation of which one's which. So if this one's 4, and I want to find, and so I know charge 1 is up here. Again, I'm just doing one charge at a time. And then once I have all the forces, I can add them up and be done with it. So force 1 on 4, and I guess we know that this distance, we're just going to call it R. Again, it wasn't given the problem. I'll tell you this should be a square. It's a little rectangular looking, but assume it's a square. So great, 1 on 4, opposites repel. We start at the tip, we want the force on 4. So I start there and I draw the arrow away from 1, directly away from 1. So there you go, force 1 on 4, done, easy. Let's go with the next easy one, we'll do 3. Same exact thing, this distance is R, so it's gonna be the force, it's gonna be, start the tail at 4, point it away from 3. So force 3 on 4. Last one is that double charge. This distance now is a little bit wonkier. You could do the math for it, and it's just going to be r square root of 2. That's just Pythagorean theorem, r squared plus, so I'll just write that out because that's helpful. R squared plus r equals r square root of 2. Whatever. Again, just kind of going through everything. But the important part is that the force is going to start here and then point away from it. And this vector will be slightly, well, we'd actually have to do the math if we wanted to. So to figure out how that vector would correspond to the other ones, we'd have to do that. Well, we know it's 2q times q. There's a k here, divided by r square root of 2 squared. So that's going to end up being k 2q squared over r 2r squared. Which ends up just being k q squared over r squared. If I had done the forces for these ones on the left, it would actually be the exact same thing. Because why? This is r, this is q, so k q squared over r squared. So it ends up actually being the exact same length of arrow. So that is F24. So it turns out that F14 equals F34 equals F24. But in this problem, I didn't ask you to do the math. I'm just kind of, again, showing it all because maybe that's more helpful for some of you. Maybe it's less helpful, who can say. But now we just do tail to end. So we have not much space is what we have. I'm going to draw in this next one. So here's my charge. This is a force. I have to remember exactly what the variables were. So that one is 3, 4, F, 1, 4, F, 2, 4. So then I just take my arrows. So this one goes this way, this one goes this way, and this one goes this way. And I just draw my, so this is how you graphically do it. And then you start from the tail. So the net vector is going to be this way. Another way you could have done it is you could have recognized that if this one is purely in the x and this one's in the y and they're the exact same value, they're going to make a 45-degree vector. That's kind of a quick way of doing it. But again, you can always just do the tail to head, and get the net vector that way. So, there you go. And it didn't really matter how big these arrows were because I didn't give you any numbers anyway. So the arrow I drew here, while that looks bigger, I mean, all my arrows are kind of arbitrary because I didn't give you what Q was, I didn't give you what R was. The important part is that they're all the same relative to each other. So there you go. All right, and I'm spending a lot more time explaining these because it's some of the first times we've seen it, but as we do these more, I'm not going to do it as much. More practice. Now you have two charges of opposite signs. So this is asking for what is the direction of the net force on the charge at the top. I have a positive charge at the top, a positive charge at the bottom left of it, a negative charge at the bottom right of it. So it makes a triangle, an equilateral triangle. And then the answers is A is up. Oh, and there's E, none of these. That's hidden there at the bottom. Secret option E. Alright, give like 5 more seconds. Most of the people responded, so 5, 4, 3, 2, 1. Alright. So we're going to do this problem the exact same way we did the last one, so I'm going to just label them 1, 2, 3, just so I can draw them easier. So here's my third one, here's my first one. Same thing, I just drew the 2 because I'm just treating those by themselves. Opposites repel, start the arrow at 3, point away from 1. There you go, so force of 1 on 3. Now I draw my negative charge. Same thing, start the arrow at 3. Are they opposites or are they the same? They're opposites, so it's going to point towards 2. So that's force of 2 on 3. Now we have to quickly think, how do these arrows compare? Are they the same amount? Is one bigger than the other? Well, because this distance is the same as this distance, and the charges are all the same value, F13 equals F23. I'm going to move this 3 over here so it doesn't... And so then we could just do our vector like this. We know they're the same size, so bam, bam, there's our net vector. D. There you go. All right. Moving forward, not going to deal with that one yet. Okay. Now what I want you all to do, so I'm going to kind of make this problem up. It's the same, going to be the same exact situation. And I want you all to practice this. And then I'll come in and do the final answer. So it's one thing to do it conceptually, it's another thing to do it mathematically. What is the value of the force on... I'll get out of here, design thing. So this is one, you're not going to respond with clicker, you're just going to kind of try to do it and you think, what is the value of the force on the top charge if Q equals 3 coulombs and R equals 2 meters? And I'll go ahead and draw the parts that we're missing here. So this is R, this is R, this is R. All right, I want you all to spend a little bit and see if you can do this. This is the time to test if you remember how to add vectors. If you remember how to calculate them, so this could both be testing. Do you know how to use that KQ1, Q2 over R squared? And then do you know how to add vectors? So spend a bit. Basically spend the next few minutes. I'll give you all like 4 minutes or so, and then I'll go ahead and spend the last few minutes. Normally I would go ahead and solve this before giving you all do it, but I think you all have the skills to do this. And this, again, it's a way to check if you remember how to add vectors. Yep. Huh? It is an equilateral triangle. Yep, so all of them are, so R, the distances between them. Yep. Oh. Yeah, no problem. Yeah, if you all have any questions at any point, please do ask. And there's some trickiness here. You have to figure out the angles of the forces. So I'm having you all stretch your brains for a bit. Try to use some of those skills you remembered from the previous courses, from Physics 1. It's a way to test if you feel comfortable with it or not. And I will even include the forces that we drew before. So we know that that one is that way, and we know that that one is that way. All right, so my hint, if you're stuck at all, the value of this arrow will be KQ over R squared. So if you want to figure out the magnitude of the arrow, you're going to need to do that. And again, I'm just going to use the same number notation that I made up last time. So 1, 2, 3. So this one's 1, this is 2, this is 3. So this is force of 1 on 3. So we're going to use Q1 and Q3. They all have the same value though, but just for sake of that's going to be one of your steps. My next hint, if you're stumped, is you need to figure out this angle. At some point you are going to need that, once you get your vectors, you need to add them. You will need that angle to add them. You have to use your trigonometry skills or geometry skills. By the same extension, you'll need this angle. Alright, since we just have a few minutes left, I'll go ahead and start solving it, but hopefully you at least had an idea. If you weren't able to finish it, but you at least had an idea of how to complete it, again, that's the main goal here. So, the first step, as I mentioned to you all, is we're going to find what the values of F13 are and F23. We know which way they point visually, but we're going to need the values to be able to add them as vectors. So I already told you that F13 is going to equal K, Q1, Q3 over R13 squared. By extension, F23 is going to be K, Q2, Q3 over R23 squared. Well, the nice thing is Q1 equals Q2 equals Q3 equals Q. So Q, Q, and I told you the distance is R. It's all R, so R squared. And now you just put in numbers. This is the easy part. Plugging in numbers at the end of the day, easy. It's generating this equation that is the part that you're going to have to practice. So K is 9 times 10 to the 9, so 9 e to the 9, times 3 over 2 squared. All right, this one is going to be identical because Q2 equals Q3 equals Q1. Same thing. So 9 e to the 9, 3, 2 squared. Great. I have two vectors now. You cannot just add these numbers together as is though. They are vectors which are not parallel to each other. Because they are not parallel, you have to break them into the x and y components. That's the part from Physics 1 that you all had to do a bunch of times. Takes a little bit of work, but you need to do it. So we need the sum of the forces in the x and the sum of the forces in the y. So if I want the F13x component, so F13x, F23x equals F13y plus F23y. Okay? Again, a lot of steps here, but this is very easy problem for me to ask you on a quiz or a test. Really simple problem for you to make, and it tests a lot of different things. So, if I said sum of fx equals F13x, and this is just notation, F23x, the subscript x just means it's the x component. So F13x, how are we going to solve that? Well, we know the vector looks like this. I'm going to redraw the vectors here. And we know that this is an equilateral triangle. This is kind of what I'm leave with. I'll probably end up finishing the problem next time. To find the x component, if we know this angle, the x component will equal F13 times cosine of theta. This is a reminder, why is that the case? That's because this is a triangle. This is where you need to remember your trigonometry. If I know this angle and I know this side, SOHCAHTOA, cosine is adjacent over hypotenuse. So it comes out to cosine. It is not always cosine. This is a really easy misconception that I see a lot of people make, is that they need the x component, they take the cosine of the angle. Sometimes it is the sine of the angle. Please remember that. By extension, F23 points this way, angle. It's going to end up being the same thing. I'll spend more time on this, finish this next class. We'll get through it. It's not too many more steps. We're out of time. Please do try it at home. If you're not certain how to do the rest of it, please finish it at home. That way you can check it next time when I finish it. I got you most of the way there. You can do it at this point. This is really good review. Have a wonderful weekend.